Good afternoon, this is Schweitzer. We're going to look at another video in the series of equilibrium, and we're looking at the size of ramifications of K. So what do we think about when we see a number? And we got to make sure we understand that everywhere in life, every single time we see a number, we place it on a scale, some sort of a scale, every single time. You could say if someone weighs, 50 pounds, okay, 50 lbs, that they're very small. But not if you're like a 2-year-old or a 1-year-old. If you saw a newborn or a 1-year-old weighing 50 pounds, which it can happen, you'd be like, wow, this little kid's huge. Or if you saw someone who was 99 years old, all right, you'd say, well, that's pretty old. But if you're a turtle, big, one of those big turtles, they live to be 100 and almost 200 years old. That might just be some average, middle of the road. Now, if you saw a 99-year-old cat, you'd be like, impossible. Every single time we see a number, we gotta put it on a scale of some sort. Same thing here. If you see a K value, what do I think about that? Well, again, what's my algorithm for this thing? It's K value equals the concentration of Y squared over the concentration of X. So when this reaction reached stalemate, the numbers in here equal that. So anytime you have a K value that is less than 1, it's not perfect, but less than 1 typically means it's reactant favored. If you have a K value that's greater than 1, more product favored. You should be realizing that essentially a very, very large K, very large, and it doesn't take much. It depends what scale you're on, really. A large K essentially means that we're going to completion. And this is just stoic, like we would normally do. Now again, if we're talking about things like concentration of lead ions in Flint, Michigan water, well, just having any lead in the water is really bad. So very small amounts matter. But for a lot of chemical reactions, small amounts, it's basically gone. So depending on what you're looking at here. Okay. So either way, what do I see when I see something like this? I see a reaction where it's got lots of reactant, not so much product. So let's run this through. Okay. I get different starting amounts. I could have all X. Again, if I have all X, then I'm going to shift to produce some Y. If I have all Y, I'll shift a lot to produce all X, almost all X. But now I'm somewhere in the middle. So let's see what we got here. Initial, I'm going to put my reaction on here. X plus Y. X goes to 2Y. Okay. Initial, stoic ratio, end. And I have 1, 2 of these. And I have 1, 2, 3, 4, 5 of these. So I want to just run this, and I'm going to draw an example of this. I got to follow the stoic ratio here to make this work, so I'm going to lose 4 of these to get 1. Cannot go to 0. Even though I'm fairly rich and favored, I'm then going to gain 2 of these to 4. Okay. Cannot go to completion, so I'm going to have 4 X's and 1 Y. That would be one example of what I can get. This guy, I'd be like, whoa, that's a really big K value. Essentially, this is like stoichiometry. Essentially, for all intents and purposes, X and Y might disappear. Okay. Depending on what you would have, I would say, a limiting reactant. But we're not going to do it that way. We'll just run it, leaves some of everything present. X plus Y yields 2Z. And there is a 2 there. Okay, so my algorithm for this guy, K equals concentration of Z squared over concentration of X times concentration of Y. Okay, let's run this thing through here. Let's try it out.
So I need to get z's. So initial stoichiometric ratio n, I'll fit this in here. I don't have any product here. So 1, 2, 3, 4, 4 y's. 4 y's. And I have 1, 2, 3 of these guys. Now remember, I can't go to 0. Okay, so how would this work? What do you think? Well, I'm going to lose, let's just lose 2 of these to get to 1, lose 2 of these to get to 2, and I'll gain 4 of these to get to 4. And that looks like my best option. I'm going to run this thing as far to the right as I can, but without running out of anything. So now I have 1x, I have 2 y's, and I have 4 of these. 1, 2, 3, 4. So size of k, important things that we got here out of this thing. There's a couple things I highlighted here. One is the size. That matters. And you should note, when I shift from reactants to products, initial to end, I'm following the stoichiometric ratio. The stoichiometric ratio must be followed. There's a couple worksheets on here, that stuff we'll do here that will emphasize that as well. But the stoichiometric ratio is really important at this point. Lots of good questions coming about that. Alright, how do we go about looking at the K value, and it can be manipulated at times? Okay, so on this situation, what happens if I take my reaction, okay, again, for a equilibrium situation versus a completion situation. Completion situation, we don't have a hard time figuring out who the reactants are. The reactants are on the left-hand side because everything flows to products, and we just put that on the right. This goes to 0. But now, in this situation, we have a forward and reverse reaction where they're both taking place, so really the product is no better than the reactant. And we literally get to pick what we want to put on which side. So the reactants literally is what we put on the left side, and the product is what we put down on the right-hand side. That's all it is. So there's nothing wrong with me writing this reaction like this, turning it around. Sometimes in specific areas of chemistry, we might flip it around because we like it better that way. It just works better for us. Either way, when I flip it, this K value is equal to the concentration of Z squared, or divided by the concentration of X squared, divided by the concentration of Y. There we go. What's this one going to be? Well, it's just flipped upside down. The K equals the concentration of X squared times the concentration of Y times the concentration of Z squared. So it's just got flipped upside down, or reciprocal. In this case, the K old reciprocal equals the K new. And that's something you'll see. So 1 over 10 equals 0.1. If this reaction is more product favored, then when I flip it around, I should have more reactant favored, which I do. Okay, what if I multiply all my coefficients? Nothing wrong with that. Perfectly legitimate. So now I have this. K equals the concentration of Z to the 4th over the concentration of X to the 4th, concentration of Y to the 2nd. Everything just got raised to a power of 2 because I multiplied it by 2. That's important. So whatever you do, whatever you multiply or divide by, we're going to simply increase the power to that level, or add that to the power. So now, K old to the power of 2 equals the K new. It's only power of 2 because I used 2 to multiply all the coefficients. So it's 10 to the power of 2 equals 100. Okay, well, what about this guy? Now, I'm going to change this one because I meant to change it. I'm going to do it quickly because I want to do that one. Alright, and let's do this guy 1/2, and we'll do this one as nothing. Alright, so there is really nothing wrong with this one either. Okay, I cut all my stuff in half. Perfect. What does that mean? Alright, so I have to raise my power to 1/2. So this is going to be my K old is just raised to a power of 1/2 equaling my K new.
you should be keenly aware that raising something to a power half is the same as square rooting. So 10, the square root of 10, is my K nu. And you can leave it at that, or I think if you plug it in, you're going to get about 3.16 or some running number. Okay. All right. So, last thing we have here is that what happens if you have multi-step reactions? We're going to see this come up again in our chapter right around Christmas time called kinetics. And that's one of our chapters that's relatively new, kind of like this chapter. What if we have multi-step reactions? Okay, well, we want to add up reactions, and that means that this reaction happens, and this one happens, and then this is the net result. So, a couple things we want to make sure. Make sure these two reactions add up. So, if they do in fact add up, then this guy multiplied times this guy will equal K1 times K2 equals KW. This is not on your laminated sheet, and sometimes if I don't use this for a while, I forget it. And so I might put that on my laminated sheet to remind myself. Okay? But before we can do this, you got to make sure it adds up. So the first thing I would do is, do I need to flip a reaction? We just talked about on this previous page that we can flip reactions, no problem, and we can multiply or divide coefficients. So, do I need to flip it? Well, all I'm going to do here is realize that just check one reactant. Make sure that reactant is on the correct side. They're both on the left-hand side, so this reaction is running perfectly fine. This guy here is NH3 is a reactant, and here it's a reactant. Wonderful. Okay, second thing is numbers. Do I have the correct amounts? Just pick one of them. I have 1 Ag and I have 1 Ag. NH3, I got 1 here, but I have 2 here. Let's try another one. This guy is, here is 1, and it's 1 there. And this guy, that looks good. Like that says it should stay the way it is. Well, this guy is not even in the reaction. Well, this guy is going to cancel that guy. So a couple ways we can tell if we're set up correctly for numbers of things. It canceled nicely. 1 cancels 1. That has to happen. So that to me says my numbers are fine. Why is there a 2 here? Well, I got 1 here and I have 1 here. So my numbers, and it's not flipped, so everything is set up nicely. If I had to flip something, I would reciprocal the K value. If I had to multiply something, I would raise it to a power of 2. But then in the end, if I want this guy, I'm going to multiply them together. So let's do that. 2.0 e to the third multiplied times 2.0 e to the third again. I have an 8 here. 2 times 8 is 16 e to the 6th, or 1.6 e to the 7th. Again, every time we look at a number, you should realize that this is big. Oof, big. It's up there. Okay, so that means I have more products. I got lots of this stuff, not so much anything else. So the reaction just is running. You can look at this thing over. Which Ag species is highest in concentration? So it's this guy or that guy? Well, it's this guy. And why? Because we have a huge K. And I want to pick out which one it is, and this is going to be this answer here. Okay, that is it because I have a large K value. All right, best answer. All right, this guy. Again, we're going to talk about this idea we just introduced last slide, is putting steps together. Okay, so I'm going to write this out just to kind of see how this works, so you can see it. So it's going to take a little bit, but you can follow along on your own. I want to get this reaction. So La is a reactant here, and it's a reactant here. So I'm going to leave it the way it is. La plus 3 plus OH negative plus HCO3 to and from LaCO3 plus water. Okay. What about this guy? Well, this isn't even there, so I can look at it in terms of canceling something else. It's going to cancel, or I can pick a different one. This is a product, but here it's a reactant. And you notice that this has to cancel, and it's canceling with that guy. And they're on the same side, they're not going to cancel. So this is going to get flipped. We're going to flip this guy. When you get good at this, you don't have to rewrite it out. But H plus CO3 minus 2 goes to HCO3 minus 1. This one gets
flipped. Yep, so flip it means you're reciprocally. And this guy, okay, what's here? None of that's in the product, so everything is going to cancel. Just pick one up and see where it cancels. The water's here, and it's got to cancel water here. So that's just fine. H2O, to and from, H plus, plus OH negative. Now let's look at quantities. So LA, got one LA, I got one LA, LA plus 3. One of these guys cancels out one of these guys. So they're on the opposite sides now. This is going to cancel that. And then water will cancel one water. And one of these guys, well, everything cancels. So my numbers are good. You should note that when you cancel things out here, you're going to get this. Alright? The water cancels. This guy cancels. The hydroxide cancels. The H plus cancels. And what I got left? One of these plus one of these yields one of these. And that's my reaction. So now, all of these reactions will add up to the K value. So it's going to be K1 times my Ka, the second one, which is 1 over Ka times Kw. When I multiply those together, I get K1 times Kw divided by Ka. You just got to pick out which one it is. And it looks like this one right here. Hold on. Is that what I got here? This one right here. Wonderful. K1, KWK. Perfect. K. Alright. There's my answer key for that one. And we'll end our video there. Thank you very much.